Hello everyone, welcome to the 26th lecture for the NPTEL course on computer system optimization for machine learning. We will go over the brief recap of the previous lecture and then we will continue on acceleration of LLM. After that we will discuss about speculative decoding. So in the last lecture we first discussed how inference and training happened for LLMs, and then we discussed about linformer, which reduces the complexity of this inner matrix from order of n squared to order of n. And then we also saw that with that particular optimization there is not much difference in accuracy, but there is huge improvement in latency as well as the memory saved, right. So let us see another acceleration technique of LLMs. So the name of this technique is FlashAttention. Again, this is a paper which is like very popular. So FlashAttention is the acceleration of training. I mean, although it is an acceleration of training, but it can be used for inference also, right. Now for a standard attention implementation, if you look, if you remember, we had this attention of QKV, which is nothing but softmax of QK transpose over square root of dk multiplied by V, right. Now remember, these numbers or these matrices Q, K, V, etc. are huge matrices, okay. And then I mean, they are huge matrices is one thing, and another thing is that they are there for each of the encoder and decoder layers, correct. Now there is very less chance that we can have those matrices saved in the cache, like in the local cache L1, L2 or even L3, right. It has to be there in the HBM, correct. Now whenever we perform the multiplication, we need to like load those matrices in blocks, right. If you remember, we discussed about tiling during systolic array, or not even systolic array, we discussed about tiling for matrix multiplication, right. So the concept is similar, like whenever we are fetching these Q, K and V matrices from HBM, we need to fetch it in tiles. We cannot fetch the whole Q, K, V matrices and perform this attention computation, right. So this particular algorithm shows the steps or the process for standard attention implementation, right. Now to begin with, we require this Q, K, V matrices which of size n by d in HBM, okay. N is sequence length and d is the embedding size, right. Now as I was saying that we cannot load the whole Q and whole K, so we have to load Q, K by blocks from HBM, right. And then we can compute this S equals to QK transpose, which is the intermediate product, right. And then we have to, again, nothing is free, we have to write that S to HBM. So S is also big, this S has to be computed for many blocks, right. So this S is written back to HBM. Now so it has to be done for all the QK blocks, and then we have to read this S from HBM, and then we have to compute P is equal to softmax of S, because if you see it is there, and then you have to write P to the HBM. Why you have to write P to the HBM? Because another matrix multiplication is coming up. So the whole softmax of QK transpose over square root of dk is P. So we have another matrix multiplication P multiplied by V is coming up, right. So that means we have to write, we already have written P to the HBM. To perform the matrix multiplication between P and V, we have to load P and V by blocks from HBM. We have to compute O equals to PV, because again O is the intermediate values, right. Write O to HBM, return O. So that is the whole process of this attention computation. Now if you look closely, there are too many HBM access, right. So there are too many HBM, lots of HBM or memory accesses, and I probably told you many times that HBM access is very costly in terms of latency as well as energy consumption, because if you remember, I mean, why? Because we have this compute unit where you have multiple of cores, and then HBM stays separately. It is an off chip memory, right, and the connection between this SoC and the HBM is through metal wires, correct. whenever we have connection through metal wires, that will dissipate lot of power, it will consume lot of energy, and then the latency is also high, right. So, any access like read or write, anything is very, very costly whenever it is done to and fro HBM, right. This is one observation by the authors of FlashAttention. So, now the thing is that we can do tiling like so. I mean, here in this particular technique FlashAttention, they introduce tiling. Okay. Now, one major challenge of the tiling is, I mean, we can split QKV into blocks. You can load them from slow HBM to faster SRAM, but remember there is softmax, right. We cannot say that we will just do those QK transpose multiplied by V in blocks and somehow we will just arrange it or somehow we will just merge it. We cannot do that. If it is just multiplication, like if it is just QK transpose multiplied by V, then we could have split this QKV into blocks and then we could have merged at the end, right. But this is not just matrix multiplication, we have this softmax around this QK transpose, correct. So, that is why I mean just regular tiling won't work, correct. So, that is why what they are doing is, yeah, they are computing the attention output of the block, then they are also keeping track of extra statistics for softmax, okay. So, they have, I mean we should not say it error term probably, but you can think that if we just do QK transpose multiplied by V and then apply softmax on top of that, or sorry, I mean if we just take this QK transpose in terms of block and then apply softmax and then multiply by V like a block of V, then there will be some error, right. So, you have to compensate that error, correct. So, in FlashAttention they introduced a technique which compensates the error, right. That is one technique introduced by FlashAttention. Another proposal in FlashAttention is recomputation. So, remember whenever we are performing the training, in training there is a forward pass and then there is a backward pass, right. Now, in the backward pass or during the forward pass, we are computing this S, which is QK transpose, and then the P is softmax of S, right. So, typically we need to store them, that is useful for backward pass, right. But then they say that we should not actually store them. I mean if we store them in the HBM, then again there will be lot of HBM access which will increase the latency as well as the energy consumption, right. So, instead of storing, we can actually recompute them, right. Again, I mean recomputation will happen in terms of tiling, okay. So, these two are observation and these two are the main proposal of FlashAttention. Now, let us quickly see the FlashAttention algorithm. Again, I mean since I want to cover many of these kind of topics, I am not going into the detail, but please go over the paper. You will see more explanation, more like proofs how it works in detail. So, I will just tell you in a very high level how this FlashAttention algorithm works. So, you see this FlashAttention requires this matrices of QKV in HBM and then let us say on chip SRAM is of size M. Now, with this N, D and then on chip SRAM of size M, we can set the block sizes which is BC and BR, okay. I mean the block size which has to be fetched from the HBM, right. Now, the next task is to divide this QKV into the number of blocks, which is the TR and TC is the number of blocks. So, TR is nothing but N over BR and TC is N over BC, right. Then we can load each of these KJ and VJ, each of these blocks from HBM to on chip SRAM, right. Because remember our goal is to, I mean we already divided that QKV into blocks. Now, we will fetch those blocks one by one, perform the softmax of QI KJ VJ, sorry QI KJT multiplied by VJ and then compensate the error. So, the first step is to load this KJ and VJ from the on chip SRAM. KJ and VJ nothing but is at the jth block of K and V, and then the next step is to load the Qi, Oi is the intermediate output, Lm are the error compensation term, which will come very soon. They needs to be loaded from on chip SRAM, and then you can see that Mij, this rho max of Sij is computed, then Pij is this exponential of Sij minus Mij, Lij equals to rho sum. So, all these things are part of the attention computation. I mean, you can do a pen and paper computation, you will see that if we fetch them in blocks, then we need to keep some extra statistics. So, all these rho max and then this rho sum are the extra statistics which has to be tracked, because now we are performing this computation by blocks, right. And then finally, whenever we have this OI, then this OI is put into the HBM, and then we keep on updating. So, we just need to keep track of one statistics, I mean one set of statistics, which is Li and Mi. We do not need to like that size of that statistics, which needs, whenever we say statistics, that means that is some that is some error compensation term, right. The size of that term does not like increase, the size of that term does not grow with respect to the sequence length. So, that is fixed. So, Li and Mi is fixed, so we update them. So, again they are kept in the HBM, and this process goes. So, you can see that what actually you are doing, instead of doing this softmax of Q k transpose multiplied by V, I ignored that scaling term, we are actually performing softmax of Qi kj transpose multiplied by Vj, and then we are also keeping track of some statistics, so that not summation, the I will still write summation, it is not summation, it is just like aggregation, let us say aggregation of all these Qi kj transpose multiplied by Vj is same as the softmax of the whole thing, Qk transpose multiplied by V. Okay. So, that is how this flash attention works. Now, let us see some results of flash attention. Again, the thing is that, if you remember in the last lecture, I told that whenever we have some optimization of this kind, we need to show that the accuracy is preserved, that is one thing, and then we also need to show that there is good improvement in terms of latency as well as memory, or like efficiency, computation efficiency, right. So, in flash attention, remember that we performed exact computation, we did not do any approximation. So, whatever extra statistics and all those things we discussed, they are not approximation, they are there to perform exact computation. So, there is no degradation in terms of accuracy, right. Now, let us see what is the improvement in terms of training, right. So, in this particular slide, I am showing you the forward plus backward runtime of standard attention and flash attention for GPT-2 medium, that is a large language model, where the sequence length is 1024, there are 64 heads, they use 16 threads, batch size of 64 on ampere 100 GPU, right. Now, remember we discussed about recomputation, right. So, you must say that okay, if we do recomputation during training, then we might increase the latency, right. Apparently not, but of course, whenever we say the number of gigaflops, that is increasing, the number of floating point operations, that is increasing. In the standard attention, the number of floating point operation is 66.6, but in the flash attention, the number of floating point operation has been increased 75.2. It is like almost 13 to 14% increase in terms of number of floating point operation. And why this number of floating point operation is increasing? Because remember, in flash attention, we are recomputing the activations, which was anyway computed in the forward pass. We do not want to store them, that is why we are recomputing during the backward pass, right. That is why the number of floating point the giga floating point operation is increasing, which is understandable. Now, remember, in flash attention, they do not need so many HBM access. if I go back to the algorithm, they just reading once, writing once. In the original attention algorithm, there were so many read write from HBM, so many HBM accesses, right. So that's why at the end, as a result, the HBM read write in terms of GB is very low in FlashAttention. In standard attention, it needed like 40.3 GB HBM read write, where FlashAttention needs only 4.4 GB of HBM read write. That's the HBM access, the amount of HBM access. Since they are reducing the HBM access by almost like 9 or 10 times, there is a huge improvement in the runtime. From 41.7, they improved the runtime to 7.3, which is like 5 to 6 times improvement, right. Now, the moral of the story is, again, we might think that all these LLMs etc. are all about computation. No, they are all about memory. So see, even if some algorithm, FlashAttention in this case, even if they increase the computation by a small amount, they have done some optimization in the memory, that the memory access is very less, and that is showing, or that as a result the runtime is now very less, right. So again, I mean, the bottom line is, we should not think that all these algorithms are all about computation, rather they are all about memory. I mean, whenever I say they are all about memory, means memory is the bottleneck, right. Why? Because whenever we say memory, we are talking about the off-chip memory. Off-chip memory is it's like lot of latency, and as well as the energy consumption is there, right. Now that's FlashAttention for you. With that, let's go to the next topic, which is speculative decoding, right. So before we go to the speculative decoding, let's quickly just recap about this LLM inference. Now we are talking about decoder only model. So decoder only model is similar to encoder decoder model. You can just think that there is no encoder now. The decoder only does whatever the encoder was doing, and that is called prefill. So whenever you provide a prompt, that prompt is first passed on the decoder. They perform the all the self attention and all those things. That is called prefill. Okay. Now let's say the prompt is the cat sat, right. Now in the forward pass, what will happen? The cat sat is there, and then in the last layer, all the probabilities of all the tokens will be computed, and whichever token has the highest probability, that will be taken as the next token. So let's say the token on has the highest probability, so the next token is on, right. And again, from on, again we will compute the probabilities in the last layer. So whichever token has the highest probability, we will take as the next token, which is a, and then after a, let's say the next token is mat, and then finally the next token is end of sentence, right. So that's how this LLM works, correct. Now one important thing here is, to generate 4 tokens, we generated these 4 tokens. Don't neglect this end of sentence, that is also a token, okay. To generate these 4 tokens, we actually performed 4 forward passes, correct. Now the question is, I mean, that means if we want to decode k tokens, we need to perform k serial runs, right. The question is, can we somehow decode several tokens in parallel? If we can do that, that will give us a huge performance benefit, right, huge benefit in the latency. Now let's see how can we do that. So let's say instead of generating a token, let's say we can guess a token, or we can guess multiple tokens, okay. Now how we can guess? We will come to that magic later. Again, let's say the input prompt is the cat sat, and then we guess that the next tokens will be on the chair, okay. We just put it on the chair, that's guess. Somehow from somewhere we got the guess, right. Now we have to run one forward pass with the guess completion. So remember, like if we have all these tokens generated, we can just run one forward pass with the LLM to see what should be the corresponding token. So, when we say one forward pass, that means we can do that masked multi-headed attention, right. So, that we can see what should be the next token with respect to SAT, what should be the next token with respect to on, and what should be the next token with respect to the, right. So, that can be done in one pass. We do not need multiple forward pass. In one forward pass, we can actually verify whether the generated tokens were correct or not. Remember, the prefill or the prompt has the cat SAT, right. Now, from SAT we can see whichever token has the highest probability. We saw that the highest probability is with the token on, and we also guessed the next token as on. So, we will keep the guess, right. Similarly, from on, we will accept the guess, right. From on we will see what is the next token with the LLM, okay, that is the token with the maximum probability. Now, here we see that the token with the maximum probability is a, but we guessed the, right. That means there is a mismatch. So, it does not match the guess, we will reject it and then we will put a instead of the, right. And then again from a we will move forward, right. But here the beauty is we actually did one forward pass, right. So, all these probability values are actually generated in one forward pass, and we are just matching that whether the next token is correct or not. We just did one forward pass, but got two tokens generated, correct. Now, that is the beauty. So, we had a guess and then with the LLM we could verify the guess in one forward pass. We did not need two forward pass to do these tokens. Okay. Why we did not need two forward pass? Because we had the whole sentence or the whole sequence ready. So, we can just do masked multi-headed attention to generate the next tokens or to verify the next tokens and all those things, correct. So, that means in one forward pass we generated two tokens. So, that is the beauty of this technique. Now, again we saw that we have this, the cat SAT on was correct, but the was not correct. So, we rejected chair and end of sentence. Then new input prompt is now the cat SAT on a. Again we will keep on guessing. So, let us say the next case is stable, probably we will also reject that, because if you remember the correct thing was mat, right. Now, when can we guess, right? That is the main question, like when can we guess? The answer is we can guess. Again it is a very intuitive thing. We can guess correctly if our question is correct. If your question is simple or if your question is easy, then we can guess correctly, right. So, for an example, let us say I tell you that my input prompt is I am at Indian Institute. Now, the next word is of, okay, and that is very easy to guess, like I am at Indian Institute of. That is the next token or next word which should come after Indian Institute. That is easy to guess. But then if I ask you to guess the next token after of, that is difficult to guess, because there is Indian Institute of Technology, Indian Institute of Science, Indian Institute of Management, many things, correct. So, the next token is science, because I am at IISc, I am at Indian Institute of Science, that is the next token, but that is difficult to guess, because there are so many options and you can only guess if you capture the context correctly. But here, to guess this token of, you do not need to capture any context. You already know that I am at after Indian Institute of, that should be off. That will anyway complete this sentence in a correct grammatical order or in a correct grammatical manner, right. So, here to guess this off is very easy, but to guess this science is difficult. So, similarly, let us say there is a translation task from Hebrew to English. Although if, and let us say that translation in English is the president was Barack Obama, right. Let us say you do not know, we do not know Hebrew, right. Then that means it is very difficult to guess this word president, right. I am guessing that this particular Hebrew script translates to president. it is very difficult, you cannot guess. If you do not know Hebrew, you cannot guess. But as soon as you get this word Barack, it is very easy to guess that the next token will be Obama. You do not need to know Hebrew, right. So, you can just guess based on the last token. You do not need to know the whole context, but for the president, to guess the word president, you need to know context as well as you need to know this whole Hebrew language. To guess this word Obama, you do not need to know the context. You just see Barack, from Barack you can say that okay, the next word or the next token will be Obama. So, that means some tokens are very easier to guess than others, and that is when we can actually use a much smaller model that we call draft model to get easy token. So, we can say that we have a target model which is a large model, let us say that is a 7 billion or even 70 billion parameter model, but with the same time, at the same time we can have a much smaller model, let us say 7 billion or even 1 billion parameter model, which will perform the guess, right. And since the smaller model has less number of parameters, the intuition is it will take less latency to generate the guesses, right. Now, another example is like, let us say I tell you a group of flamingos is called, to know the next word or the next token is a, which is very easy, right. We can use a draft model to guess the token a, because again it is English, you do not need to actually know what is a group of flamingos is called. Now, let us say the draft says flock, usually the group of swan is called flock, right, but the group of flamingos is called flamboyance, which is a difficult thing to guess. You need to know much more English, you need to know the context, right. So, here to generate this word a, we can use a small draft model, but to generate the word flamboyance you need to use a target model, or you need to use the large model, right. So, that is the speculative decoding. With that I will end this lecture. In the next lecture we will continue this speculative decoding and we will see more nuances of speculative decoding. Till then, thank you very much.